Okay, so what we're going to do today is we're going to look at the acid and base properties of salt solutions. Now, I want you to take out your packet, which is this, right? And I think I'm going to make room for both. And I want you to have this flow chart. This flow chart is really useful. You can't have it on the test, but it will help you kind of organize your thoughts so that you can figure out how to categorize these salt solutions as acids or bases. Now remember, I'm going to go back to this problem here. Remember here we used a salt to deliver an anion, and that anion had a basic property. We also we have many anions that could be basic. We also have cations that can be acidic. And so what do we do if we have a salt? Some can be neutral, some can be acidic, and some can be basic. So a salt. So that's what we need to look at next, are the acidity and basicity of salts. Okay, now when we first started off, we talked about the strongs. So a solution of salt can be classified as acidic or basic. When an anion reacts with water to generate either a proton or hydroxide, this reaction is called hydrolysis. So sometimes this will be referred to as salt hydrolysis. So here are all the anions of the strongs. Now, the question is, if these are the conjugate bases, so do these 6 ions act as strong bases? The answer for this would be no. Why? Because the conjugate acid is completely strong, is completely dissociated. This is not going to pick up a proton from water and go back to hydrochloric acid or hydrobromic acid and so on. That's not going to happen because it's one arrow, and that arrow goes in this direction only. It is not going to go back. So, do they act as weak bases in solution? No, they absolutely do not. How do these ions affect the pH? They don't, because they don't do anything. Once we've made them, they just sit there. So they act as spectators or neutral ions in acid-base reactions. Okay. Now, let's look at some ions that aren't necessarily neutral. So it says here, write an equation for the hydrolysis of acetate ions. So this is acetate plus water gives acetic acid and hydroxide. Okay. Now, based on this, if I dissolve the sodium acetate in solution, right, this, the acetate will behave as a base. The sodium acetate, in this case, is going to be a base. Why? The sodium is going to be a spectator. That's a nap. We don't worry about that. But this, once the sodium acetate is dissolved in water, it's going to go on, pick up a proton, generate hydroxide, and off we go. So what happens then, a sodium acetate solution is going to have a pH greater than 7. Okay? Now, let's look at this anion. This anion can pick up, release a proton as an acid. Not a very good chance of that, right? 10 to the minus 13. Or it can act as a base and pick up a proton, generate hydroxide, and there's my Kb. So in reaction 1, the hydrogen phosphate ion behaves as an acid. In 2, it behaves as a base. So which is it? Which one is going to be preferred, right? So if I have sodium, so I'm basically taking this, I'm putting it in solution, I get 2 of these plus HPO4 minus. What's it going to be? Is this going to be acidic or basic? Well, basically, I can look at these two quantities. Ka is much, much smaller than Kb, which means there's a preference for this reaction over that. So when I drop this in solution, the salt, this is going to act like a base. And so for that reason, this is going to be basic because Kb is greater than Ka. That's another salt. Now, let's look at ammonium ion. Now, ammonium ion is going to act like an acid, right? And water is going to pick up a proton from there. We're going to get ammonia and hydronium ion. And so it says the Kb of ammonia is equal to 1.8 times 10 to the minus 4. Kb, what is the Ka? So let's do that because basically this is Kb is going in this direction, right? That's Kb. We're going in this direction. So remember that Kw is equal to Ka times Kb. So Ka is going to be Kw divided by Kb, which is 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, and that equals 5.6 times 10 to the minus 10. Right? So in this case, the Ka for the acid is 5.6 times 10 to the minus 14. So what that means is NH4 plus can act like a very, very weak acid. All right, so we're going to hit the pause button on that. So we're just collecting data here. Now these cations do not react with water, therefore no effect. They are neutral. Now, there are some exceptions for cations. You saw that ammonium ion can act as a weak acid. These are neutral, but there are a couple cations that can. They're down here, and I'm going to come back to this table in a minute. Basically, what happens is iron can coordinate, it's called, with water. And what happens is one of the protons off one of the waters comes off. And I can get this plus H3O plus. Now, if you notice, these are the ones that can do that. These tend to be in the transition metals section of the periodic table. These are group 1 and group 2. These are neutral. But when you start getting aluminum, chromium, and iron, then you are getting into the possibility that these cations can act as acids. Now, this is a table. What we're going to do is if you're given a salt, let's say, you're given a salt, and I'm going to give some examples. You're going to dissolve the salt in water, and a couple things can happen. Either you're going to dissolve it, and the cation and the anion are neutral. You're going to dissolve it, and the cation is acidic and the anion is neutral. You're going to dissolve it and the cation is neutral and the anion is basic. You're going to dissolve it and you could have an acidic and a basic cation and anion. How are you going to know whether that salt is acidic or basic? So I'm going to stop here and I'm going to show you this flow chart. I'm going to work some examples, and I think this is really the best way to sort through this. So I thought the easiest thing to do is to kind of go to this part. We're not doing Lewis acids, so they took those off the test, so we're going to do here. Examples of acidic and basic salts. Okay, so let's go through the flow chart. Let's take a real simple one. Sodium chloride. All right. So you go to your flow chart and you say, okay, is the cation the conjugate acid of a weak base? Any kind of amine or these cations? No. So I'm over here for sodium chloride. The cation will have no effect on the pH. It's sodium. Is the anion the conjugate base of a weak acid? No, that is not. Cl is a conjugate base of a strong acid. The anion will have no effect. The salt is neutral. So this is a neutral salt. All right, let's do another one. What about this one? Okay, this is ammonium chloride. I go up here. Is the cation the conjugate acid of a weak base? It is. It's ammonium. So I'm over here. The cation is acidic. It will undergo hydrolysis reaction in water, which we just saw, and it will donate a proton. All right. Is the anion now? So we know that the cation is acidic. What about the anion? Is the anion the conjugate base of a weak acid? It is not. It is Cl, which is the conjugate base of a strong. Therefore, the NH4 takes precedence. It is acidic. Cl minus is neutral, so this salt is acidic. Let's do another one. Let's do a more complicated one. Okay. All right. So now we've got ammonium, or NH4, ClO2. All right. Now, the cation is the conjugate base of a weak, the conjugate acid of a weak base. So yes, we're over here. Now, however, though, this anion, which the anion would be ClO2 minus, this is, ooh, sorry, I put the 2 in the wrong place, didn't I? This is the conjugate base of a weak acid. Weak acid being that. So I'm over here. Now what that means is my cation is acidic and my anion. How am I going to figure out what it's going to be? So basically what you have to do is find your Ka of this, and that's 5.6 times 10 to the minus 10, and the Kb of this, which is 9.09 times 10 to the minus 13. And you see which one wins out. This one wins out. This Ka is higher than this Kb. Therefore, this salt is acidic. Let's try one more, and then I'm going to have you work some examples. I made a little formative assessment for you to kind of work through this. The best way is just to practice. All right. Now this one's, again, going to be over here. It's ammonium. We also have the conjugate base of a weak acid. But let's look at our Ka and our Kb for this one. Now, for NH4, the Ka is 5.6 times 10 to the minus 10. And for IO minus, Kb is 5.0 times 10 to the minus 4. This really is takes precedent, so this is basic. All right, let's do one more. I want to do sodium acetate, which is on here. So sodium, of course, is not ammonium or one of these cations, so it is not, we're going down this side. The cation will have no effect. Let's look at our anion. Now, in the last case, we had sodium chloride, we went off in this direction. But in this case, is the anion the conjugate base of a weak acid? It is. The reason for, so we have sodium, we have acetate. That means the anion is basic. That means this salt is basic. So I think I went through all the different scenarios with you. I've got a formative assessment that you're going to work on that shows all the, kind of lets you practice. Once you get the hang of this flow chart, these problems will be really easy for you.